Hello everyone. Before I start with this module, welcome to those of you who have just discovered this channel and this series. There are more videos in this series, so check out the playlist at the end of this video if you want to see the rest of it. For my existing viewers, welcome back. Let's get into Module 5, Enterprise Network Security, where we're going to look at some things that will help you do better architecture and design practices when it comes to network security. So, first section, concepts and some considerations. First and foremost, let's get some general network architecture and infrastructure concepts out the way. And the first one is the network exists to meet business objectives, first and foremost. Our cybersecurity shouldn't detract too much from this. Remember, security often does come at the cost of performance, and we do need to balance that when it comes to the network. We can have the most secure network in the world, but if it works super slowly, no one's that interested in it. So, moving along. We need to be careful when we select and place our devices, as it's going to have an effect on the actual effectiveness of the security, but also, let's not forget, the performance of the network. And this will include everything ranging from the actual physical network media to the appliances and the configurations that we choose. We must also bear in mind as well that the user workflows must be understood and looked into so that we can make better choices around our network design and the implementation of the security for that design. And some things you might want to look at is that the closer the users are, both physically and logically, to whatever it is that they're working with, the easier it's going to be to keep things secure without compromising the performance too much, as you'll have less of the network to worry about when it comes to interception, rogue devices, unauthorized monitoring, stuff like that. But this is not always going to be practical. Still worth us trying to do though. Now, from another concept perspective, let's bring in our good old friend in networking, the OSI model, or the Open Systems Interconnect model. Now, usually we use OSI to understand how networking works and also a little bit of troubleshooting. But here, we're going to be using OSI to help us with network security. Now, what's going to do us some favors here is it's going to make sure that we've got a checklist that we can refer to, seeing, okay, I've looked at this layer, I've done the following, I've looked at this layer, I've done the following. And by being able to do that, we're going to keep our blind spots to a minimum. We're less likely to forget to do something. So let's have a nice little table here. So first of all, before I climb into this table, let's just quickly acknowledge a limitation. This table is not comprehensive. I haven't covered every single thing in this table. But what I do have here gets your mind working in the right direction. So let's start with the physical layer and start working our way up. So at the physical layer, you can start worrying about things like shielding the signals that travel through our network cables to minimize on an attacker trying to use electromagnetic field fluctuations to decode the data. Another thing we can do is also look at monitoring for new clients. And the stuff we can implement from the appliance perspective would be locks on the network cabinet, keeping network termination points to a minimum, stuff like that. When we step up to layer 2, which is usually where most of your switches work, we can start implementing MAC address filtering, we could look at VLANs, and we could look at things like spanning tree protocol. Now, the benefit of these services and solutions is that they can be done on any switch as long as it is a manageable switch. And you'd be amazed the benefits that just using some of these settings can do for your network security. Sometimes utilizing the network appliances properly is as beneficial, in some ways even more so, beneficial than going and buying a dedicated security appliance like an intrusion detection system or a firewall. Then when we move up to the network layer, we could look at using things like access control lists, DHCP reservations, or even better yet, implementing a proper packet filtering firewall. Then, after that, we could look at the port filtering at the transport layer. We could look at certificates at session. We could look at some content filtering for emails, like looking for scam and phishing terms and deciding how to handle those emails that contain those. And obviously keeping our software up to date, both on the client, but most importantly, on the server. And normally when we start moving from layer 4 upwards, we start to look at dedicated servers like proxy servers, more advanced firewalls, security services running on the application services. You get the idea. But like I said, this table is not comprehensive, but it does get your mind working in the right direction. And we will obviously be able to add stuff here as we learn more about cybersecurity. Now let's jump into the basic devices first in our network, like our switches. What can we run on our switches that will help make us more secure there? Well, first up, track your switch's logical topology. You can look at your physical topology all you like, but the logical topology is going to have the biggest impact on your overall security. Things like spanning tree protocol and all its variations, as well as VLANs, will have an impact on how data flows through your network. And the thing is, the way data flows through your network is going to have some impact on where your security needs to be implemented. Now, normally what we'd recommend with our switches is to have manageable switches. Switches that you can log into, that you can configure, and control some of their behavior. Your dumb switches or your unmanageable switches are not ideal here. So let's start with having manageable switches and then implementing them in a hierarchical design. The idea of a hierarchical design is that you'll have access switches where desktops will be plugging in and where the wireless access points for wireless clients will probably be plugged in as well. Most devices, we will worry about things like MAC address filtering and other types of access control mechanisms. Then, after that, you could have a distribution layer just to spread the workload, but the main purpose of the hierarchy is to have access switches and core switches. If you want to have distribution in between, go for it. But the benefit of having the core switches is they can be high performance, they can enact topology-wide configuration and security, at least for that LAN segment. You get more choices in the design. And then once you've got that hierarchical design, you could look at implementing something like spanning tree protocol. Now, spanning tree protocol is primarily for loop prevention. But why does this help us with security? Well, if a broadcast storm were to occur, where a broadcast is able to loop around the network over and over and over again, that can lead to a denial of service, something we want to avoid, obviously. Now, with spanning tree protocol helping us here, the big benefit will be that we can have our physical redundancy, which means we could decrease single points of failure, and we would also be able to control how the logical topology is going to behave by dictating what's going to be the root switch or the root bridge. Now, you also might want to consider implementing variations of spanning tree protocol. The original spanning tree protocol might be too slow for you, in which case rapid spanning tree protocol, or RSTP, might be the better option. Maybe you want to have different STP topologies per VLAN, in which case MSTP or one of the vendor proprietary VLAN-based spanning tree implementations would be an ideal choice for you. And then, once we've done that, we could look at using a bit of segmentation. Now, the idea of segmentation is we're going to break up the switched network into groupings of some kind, whether it be based on the traffic or the groups of users. We want to separate them because the traffic and groups of users, whichever logic you prefer, both can help us with security, as groups of users usually do have common security requirements, and groups of traffic or protocols or services usually also have some kind of common security requirement. Now, segmentation or breaking up of the network can be achieved through VLANs, where you can still be on the same physical set of switches, but using virtual LANs, you can logically separate the groups of users. There is a catch, though, with VLANs. They're not perfect. Attackers can get out of them. Attackers can hop from one VLAN to another. It does take more time and effort, obviously, which might be okay for you. But if it's not okay, then you still have the option of physical segmentation or separation. Now, to achieve physical segmentation, you would probably have to bring in routers then and have physically separate switches. This will drive up the cost of your network, as you will now need more appliances. However, it does help alleviate some of the concerns of VLANs. Realistically, though, most organizations do favor VLANs, or at least a combination of VLANs and physical separation. After that, you can look at having some MAC address filtering. All switches can recognize MAC addresses to make their forwarding decisions, but most manageable switches have a capability that allows you to also apply security operations based on the MAC address. So, for instance, if the MAC address is unrecognized to the switch on that particular interface, it could either limit the operations and services on that interface or outright turn it off to prevent access by a rogue device. So we've got some pretty cool options with our switches. But all of this does rely on our switches being manageable or configurable. Our dumb or unmanaged switches are going to severely hamper our ability to apply these options and securities throughout the network. Then comes our routing infrastructure. So here we're worrying more about our IP addressing and our logical segmentation of our network. And we want to try and take as much advantage of our IP addresses as we can to do traffic filtering or screening of networks. When all the users have a well thought out addressing and IP addresses allocated to them, it makes us a lot easier for us to use things like access control lists to control the flow of traffic. Now, access control lists are a very interesting little feature that can be implemented on anything that works at layer 3. So you do get layer 3 switches that can run ACLs. You can run ACLs on your routers and obviously on your firewalls. Now, what makes ACLs interesting is that they're a glorified text file that contains a list of statements. The statements will normally be along the lines of permit this or deny this, permit this or deny this. It's pretty much the only operations an ACL does. Permit the traffic or deny the traffic. And it knows whether it should permit or deny the traffic based on conditions like source IP address, destination IP address, etc. Now, when it comes to an ACL, they're going to process in order of entries. So if the first rule or the first entry matches, that action will be applied. The traffic will be permitted or denied, and no further entries will be checked. This means that when you're creating an access control list, you've got to be very mindful of the order of the rules. If you're not, you're going to have some very unexpected behavior and outcomes. Preferably, when it comes to filtering and screening your networks, a firewall would be a better option than an access control list. Case in point, an advanced access control list will filter on source IP address, destination IP address, source port number, destination port number, and protocol. That is the stuff that a packet filtering firewall, which is considered to be a basic firewall, can do. So firewalls are more preferable, but in a situation where it's difficult to justify the purchase and implementation of a firewall, an access control list running on a router might be sufficient. However, a dedicated firewall will always be the more preferable option when it comes to a security design. Now, other things that will help us will be things like IPsec. IPsec is an authentication and encryption service available to us from the Internet Protocol. So this runs at layer 3 of the OSI model, whereas most cryptography and security actually runs at a higher layer. So this is quite cool because it means from a very basic low level, we can have authentication of sender and receiver, and we can have the encryption of the traffic payload. Now, IPsec is available for both IPv4 and IPv6, but it was originally created for IPv6. So if you're running with v6, you have IPsec running by default, protecting your traffic. In fairness, the default settings aren't the greatest possible settings, but hey, it is there. Whereas with IPv4, IPsec is sadly not running by default, as IPsec had to be retrofitted to work with IPv4. And that means that if you're using IPv4 and you want IPsec, you are going to have to enable it and configure it. But once that's done, you've got a pretty cool little security solution running at layer 3 of the OSI model. Then another interesting thing that can help us with our layer 3 security and our routing is, believe it or not, subnetting. Now, the way subnetting will help us is it does make it a little bit harder for the attacker to make presumptions about our network. If I'm an attacker and I just see the device's source IP address of 192.168.0.42, I don't know whether that's been subnetted or not. And that would affect my ability to do a network scan. It would affect my ability to manipulate routing. I would need to know the subnet mask information as well to better predict and map out how your network is designed. Now, it's not going to stop me. It's not impossible to do. But every little roadblock we give our attackers helps drastically. Also, another advantage we have is, let's say we've subnetted the network down to where it only has 14 usable host addresses. And in a particular LAN segment, there's only 13 devices at a time. The 14th device will stand out a lot more because that one last address gets used up. So it's pretty cool. Then, another interesting thing that is not directly security related but does help us is network address translation. Network address translation is that service that allows us to go onto the internet where our LAN devices have private addresses from the 10, the 172.1.6 through to 172.3.1 and the 192.168 networks. Those private addresses we can't use online. And that translates our source IP address to a public IP address that our ISP has said we can use. This helps us a little bit as the attackers on the internet monitoring our activity cannot tell from the activity of the public IP address whether it's one very busy host on the inside or many hosts not doing too much. It's much more difficult for the attacker to determine things about what's going on inside of our network when that allows us to hide behind a public address. Again, though, similar to subnetting, it's not going to stop the attacker from learning about our network, but it's going to slow them down. Now, with these two things in mind, where we can use VLANs, physical segmentation, etc. with switches and subnetting and access control lists on our layer 3 devices like our routers and our firewalls, we could now look at implementing security zoning. Now, the idea of security zones is that we are going to base these zones off of a common security requirements of the devices that will be inside of those zones. So a very popular approach would be services and groups of users. Now, when I say things like services and groups of users, I could, for example, have different departments in different LAN segments, each being a security zone. And then the security requirements of those departments affect the things we do to the zone. Now, let's run through some common zones that would be worth having. The first one would be a demilitarized zone, or a DMZ. Some people refer to this as your perimeter network. The idea of the DMZ is it's a screened or filtered security zone where you use one or two firewalls, and it's between the private LAN users and the internet. And normally what you do in your DMZ is you place things that need to be accessible by both private LAN users and public internet users. Things like, for example, maybe a remote access server, a web server if you're hosting it yourself, or something like that. And the benefit of the DMZ is when traffic's coming from the internet and targeting something in the DMZ, there'll be one set of rules applied with like a firewall. That'll be probably fairly forgiving. But if anything wants to get from the DMZ into the LAN, then the rules become a lot stricter. So that's pretty cool. Another type of zone that's normally based on services is your data center. Your data center is just the fancy term for where all the servers are going to be. The database server, the file storage server, the various servers that are used by your organization will normally be kept in a data center. And maybe you even want to do subzoning within the data center. That all depends on the organization. But you definitely want to make sure that there is a logical separation between where all the servers are and where all the users are, so that you can have better security filtering and screening taking place between those zones. Then, as I've alluded to, you've got your user zones, which will normally be based on the departments and the security requirements of those departments. Then, your public-facing zones. Your DMZ can be considered a public-facing zone, but maybe you've got stuff aside from the DMZ that needs to be internet accessible or be able to access the internet. Certain user zones might be public-facing, others might be internal users only. It depends on what you're up to. But as an example, I would probably not allow my research and development department to have much public access, if any at all, to minimize on any external threats and corporate espionage. After that, you might want to maybe have a management zone. Now, when I say management, I'm not talking about your manager that you answer to. I'm talking about things like a network operations center for managing and monitoring network services. Maybe even a dedicated security operations center where we can monitor and respond to security threats from a centralized location. But regardless, the whole purpose of all these zones is so that we can implement things like firewalls and access control lists to apply traffic filtering. Now, one thing you want to watch out for with your zones is redundancy. Redundancy between zones is great, but you want to make sure that that redundancy is not providing ways to bypass the filtering between zones. If you want to have two or more ways to get from one zone to another, that's perfectly fine. I'm okay with that. But make sure every way you have to get from zone 1 to zone 2 to zone 3, whatever, has filtering and the security and setup is consistently applied. Believe me, it'll help a lot. Next up, let's talk about our network attack surface. With our network attack surface, this is where we're trying to understand what kind of target our network is presenting to the attackers. And the things we want to look at here are the points of ingress. How would an attacker gain connectivity and access to my network? And what would the implications of those points of ingress be? So for example, you got your layer 1, layer 2 points of ingress. That would normally imply the attacker has physical access to the network and is able to get a device onto it and use a rogue appliance. This could be anything from an ordinary laptop to a Raspberry Pi to pretty much anything you could imagine. And when you got layer 1, layer 2 access, well, then you're on the network just like any other host. And that could be very dangerous. Layer 3 points of ingress would usually be where the attacker is able to manipulate IP in such a way as to gain access. Whereas anything from layer 4 upwards is normally where the attacker has compromised an application and possibly that host that is running that application service. But either way, the points of ingress is worth looking at. And the thing is, when you start worrying about physical security and physical network security, you're going to decrease the layer 1, layer 2 points of ingress, leaving you layer 3 upwards to worry about. So this is why we start to look at our network attack surface as a way of how would I get onto the network if I were the attacker. That type of mindset helps a lot. Now, some things we want to be on the watch for. Pitfalls to avoid, basically. Single points of failure. Now, this is not just from a security perspective, but also from an availability perspective. We want to minimize on catastrophic failures caused by just only one thing providing that service or that access or whatever. We want to minimize on single points of failure. I would ideally like to say I want to eliminate them all, but realistically speaking, you'll probably never eliminate all the single points of failure that could exist. Cool. Next thing we want to look for are complex dependencies. Now, a complex dependency is when you got thing A relying on thing B, relying on thing C and D rely on thing E being there. But if E is there, then you can't have thing F, which would affect your choice of having thing G. That's the point I'm making here. There's too much going on. Have as few dependencies as possible. That way, it's easier to keep track of them. It's easier to make sure that they're reliable. And also, easier to make sure that the attackers aren't interfering with how different services and appliances interact with each other. Then, focusing too much on availability. Don't get me wrong, availability in a network matters a lot, but it shouldn't be completely at the cost of confidentiality and integrity. Like I said right at the beginning of this video, we need to strike a balance between access and performance, availability basically, and security, where we're normally focusing more on confidentiality and integrity. Balance it out. The way I normally like to do this is once I've made my network fairly reliable and highly available, I then start looking at, okay, cool, how can I make this more secure now? How can I make this harder to gain access to if you're not meant to be gaining access to it? And while I'm working on that implementation of security, I try not to decrease too much from the availability that I've achieved. It's a balancing game. Then, another thing to watch out for is bad documentation. This is something I've seen time and time again where an organization has bad documentation practices. The problem is when documentation becomes out of date, it makes it harder for us to improve the network because we'll be doing improvements and designs based on the documentation, when in reality the network is nothing like what the documentation says. We need to make sure that is kept as up to date as possible and as accurate as possible. It's not the most fun thing in the world, but once we get it right and we get the documentation up to date, it will be a lot more useful to us. Another thing we need to look at as well is to avoid relying on the perimeter model of security. The perimeter model, when it comes to network security, is where we look at the enterprise network as a fortress. Everything outside of the fortress, everything outside of the perimeter, outside of the network, is untrusted. And then if something is on the inside of the network, it is trusted. We need to abandon that mindset. Think about it this way. Bring your own device where you're allowed to use your own personal device at work, for work, like your smartphone. That hooks onto the Wi-Fi. That has completely eliminated the perimeter model's whole premise of if it's inside it's safe, if it's outside it's not, because the employee's personal smartphone could have malware on it, and that malware can now just hop around the network as it gains access. Most organizations are moving away from the perimeter model and adopting something called the zero trust model, where regardless of whether you're inside or outside the enterprise network, we don't trust you until proven otherwise. So no access, no trust until authenticated. Even if you are an appliance that was issued to the employee by the organization, we still validate as a trusted device before it gets access. The old perimeter model would have assumed, oh yeah, you're inside the network, we trust you. Nowadays we don't. Besides things like BYOD, you've also got things like work from home, you've got cloud computing. All of these things are affecting the reliability of the perimeter model, so we have to basically move away from it now. Now let's look at network access control. Now, network access control, what we're looking at is how can we control users and hosts gaining access to the network. And if we can do this effectively, we'll be able to drastically decrease the ability for an attacker to gain access to the network. Now, my first and most favorite thing to do is to physically turn off unused access ports on switches. If the interface has got nothing plugged into it by design, it'll probably be better that we rather log into the switch and shut that interface down. That way it could never be used against us. We could also use MAC address filtering and MAC address limiting on the access devices, where an unrecognized MAC address will either limit the activity and access that is available on that interface, or outright shuts it down for us. That can help us a lot. Again though, it's going to rely on good documentation. But by doing this, we will decrease the ability for a rogue appliance to be plugged into the network. Another thing we can also do is the IEEE's 802.1x standard, which is basically network authentication. Various things like the Extensible Authentication Protocol, Radius, and TACACS Plus are implementations of the IEEE's 802.1x standard. And the idea is, as the device connects to the network, the user is prompted to authenticate in some way or form. And when we do that, we can then have every device being authenticated, whether it be on the wireless, whether it be wired, whatever. Now, for things that don't have users on them, don't worry, 802.1x does support certificate-based options as well. So when a server is reconnected to the network after being fixed and tamed, it will still be successfully authenticated. And one of the beautiful things is the IEEE standards like 802.1x are for the most part vendor neutral, or at least not too vendor biased, which is quite nice. Now for a pretty extreme network security concept, air gapping. The idea of air gapping, being the most extreme form of segmentation, is that we are going to physically separate and isolate devices, or even just one device, onto a LAN that has no interconnectivity with other networks. Imagine this: half a dozen computers connected together via a switch or something like that, but there is no connectivity to any other IP network. There isn't even internet connectivity. Now, why would this be useful? Well, it means that data can only be moved in or out of that network via physical media, which means unless you have physical access to one of those computers, you're not getting onto that network segment. But where would I use something like this? Well, if you've got something that is very, very security sensitive, air gapping might be an ideal option. It just means you need to move data into or out of those devices using removable media. It's also pretty useful for legacy systems. If you've got an old, outdated system that you need to use but is not safe enough to have internet access, this might be a safe way to move data in and out. Or you've got unconventional IT systems, like, for instance, an industrial control system that you know is going to be very difficult, if not impossible, to secure properly from cyber threats. You could use air gapping as a way to keep it safe and isolated. Now, yes, air gapping does take away a lot of convenience and means that routing is not really going to be a viable way to get traffic to this place. It's going to rely a lot on human beings, but hey, in an extreme circumstance, that might be ideal. And if you do a little bit of research, there are computer scientists who find very interesting ways to get data in and out of an air-gap network. Like, for example, picking up on thermal fluctuations of a CPU to work out what it's processing, malware varying the speed of a CPU cooling fan, and a microphone decoding that frequency variation of the fan. So all very cool stuff, but the problem with all of those proof of concepts that you can get data out of an air-gapped network is assuming you have physical access to those devices. And if you had physical access, then why would you go through such a convoluted way of getting data in or out of that network? There'd be much easier options. But the idea of air gapping is that there's pretty much nothing between the network and the rest of the world other than the air. And we're not even letting wireless signals travel through that air. Now, some considerations when you're busy working on your network design and trying to make it as secure as possible. Cost is always going to come into the equation. It's going to cost you money to buy appliances that are more capable, that are more secure, or purpose-built for security. It's going to cost money. And there are two ways that you need to look at the cost. The first is the acquisition of the appliance. It's going to cost you money to buy the thing, no matter which way you slice it. And it's also going to cost you money to implement. If you think, wait a minute, but I don't have to spend money to implement it. I got IT support staff. Yes, you do. And they are a salary. And that time that they spend working on that thing is taking away from other things they could be working on. So there is always a cost for implementation. But then there's a total cost of ownership. There might be recurring costs that need to be factored in. There's definitely going to be electricity and probably cooling and the electricity for that. Then there's going to be the replacement of parts that wear out and fail. There might be licensing involved. You could also look at the time spent on maintenance as, again, a salary expense. So there's going to be a total cost of ownership over the lifespan of this device. You need to consider that. Now, the costs for the device's entire lifespan are not going to be easy to predict, but you can at least make good approximations and estimations, especially if you have some historic data to rely upon. But another consideration after looking at the money is latency. Anything you do to implement security is going to slow network communications down a little bit. Anytime there is a processing device between computer A and computer B, there is a bit of latency introduced. As long as that latency is kept to a minimum and the number of devices is kept to a reasonable amount, you shouldn't experience too much of an issue. But something we can do is we can rely on the device's compute capability to improve the latency situation. A firewall with a good CPU and high forwarding capability will probably minimize on the amount of delay that we would experience. Whereas if I choose the wrong kind of firewall with too slow a CPU and too slow a network media, then that could end up becoming a massive bottleneck when it comes to performance. So please do pay attention to the network media and the speed of that network media, because it will impact how fast something can work. Yes, the security will still delay us, but we should at least make sure that the delay is as small as possible. This does not mean you go and buy the most expensive high-performance appliance possible. It means you buy the appropriate appliance for what you need. Another thing you also need to think about as well is the organization is hopefully going to grow, which means your security solution needs to be as scalable as possible. It needs to be easy to expand and enhance, either in terms of capacity or capability, or better yet, both. So you do need to consider how scalable will this design and will these devices be for me in the future. Another thing as well is how hard is it to deploy this thing? The easier the deployment, the better it'll be in the long run, because you're going to spend less time just getting it working and you'll spend more time setting up to secure you properly. So you want to try and have the deployment as straightforward as possible. Please note this does not mean, we don't want to favor a complex thing. It means if that complex thing is difficult to set up, it better give me a lot of benefit. I want to see a tangible and significant benefit to implementing a security control or a security appliance of any kind in relation to how difficult it is to implement. Another thing to consider is the availability requirements of the network and how this device will affect, or this design will affect, my availability. I want my network to be working, stable, and I want the users to just use it, not have to think twice about it. just like most people don't think twice about the roads they drive upon. Yet, the roads need to be maintained and well designed to be as available as they are and as thought-free as possible. Then, we want to make sure that we got resiliency against failure or attack, which I know sounds a bit redundant considering what we're talking about here, but we do want to make sure that if there is a failure, it either has to be an extreme situation or that there is a backup solution of some kind, like for example a redundant link, and that the network can identify and resist various kinds of attacks. But we all know that prevention is not always going to be possible, which means that we want to make sure our network designs are as easy to recover as possible. Easy to reconfigure, easy to redeploy, easy to get back up and running, or possibly even rebuilding. Another thing to consider as well is the power requirements, which is going to be a part of costing, but you also want to think about backup power. One of the most amusing issues I have seen in the recent years is users complaining that the network is not working. And that's because there was a power cut. Now, how did the user not realize that there's a power cut? Easy, laptops. Laptops are the most common end user device issued in the workplace nowadays. And if the power goes out, the laptop can then switch over to its battery straight away. And people seem to assume that if the laptop's got a battery, surely the rest of the network has batteries as well, and it doesn't always. So you want to maybe have UPSs, inverters, and backup generators to make sure that you can keep your core network appliances powered and functional during a power outage. This would allow your organization to not be affected by natural disasters as easily, and also decrease the number of options an attacker has, because an attacker could always try and tamper with the premises' power supply to decrease some of the security. If you got backup power though, your security should be adequate still. Another thing you also need to consider is what's the vendor's long-term support like. Every network vendor has a support program of some kind that you're going to be receiving patches from for keeping your devices up to date. Now, if you're buying this network appliance just at the end of its life cycle, you're not going to get that many updates, and the support cycle might be a lot shorter than you expect. Whereas when you're buying a brand new appliance that just came out last month, does the vendor have a good reputation of supporting that device for a long time? Or are they going to pretend like they're going to support it forever until the next new thing comes out, in which case then they might run away from it and abandon it, which is something that irritates me to no end. You need to look at that and look at the vendor's track record of what they've been like with previous appliances and solutions. All right, but that's just some things you need to consider while you're designing a network. But wait, how should I do the design? There is no perfectly right or wrong answer, but keeping these things in mind is going to help you create a better solution. And realistically, that's what we're always doing, is looking for something better, looking to make it better. That's the game here. It's a constant journey of improvement. Let's get into the next section. Network security, appliances, and devices. Now, before we start looking at specific kinds of devices, let's talk about some attributes for these devices. First attribute is it an active device or a passive device? An active device will normally have some sort of executable that runs and engages with traffic or hosts or something like that. Now, usually active devices will require some kind of setup, but they are more likely to give you better preventative controls. Passive devices, on the other hand, they just sit back and watch what's going on. And they will obviously react and do something when they notice something going on. But they don't need much setup, if any at all. And they're more likely to be your detective kind of controls, which I'm perfectly cool with. Then another consideration of the devices is it meant to work inline, or is it meant to be an off-path device or a TAP device, test access point? Inline devices, also sometimes referred to as gateway devices, would be something like a firewall, where your traffic has to go through the device to get to the intended destination. Whereas off-path would be more like a monitoring appliance. Traffic goes through a point, and all that happens is the off-path device just watches what's going through that point, but it doesn't actually act as a gateway. It's just standing to the side, observing what's happening. That's why we refer to them as test access points. Now with inline appliances, whether they're active or passive, it doesn't matter. They are definitely going to have an impact on performance as they need to process and forward the traffic. Whereas an off-path device is going to have less impact on performance as it just needs to be able to keep up with its observations, but not necessarily forward any traffic itself, meaning no incurred latency. Benefit though of the inline is it's more able to engage with a threat and stop it, compared to an off-path, which will probably at the best be able to just let you know, hey, something bad's happening. But as far as I'm concerned, one of the most important attributes that is never spoken about is failure. Does the device fail open? Now, fail open means that the device will prioritize availability under a fail condition. So if something goes wrong, the device will keep working and probably give open access. An example of this, where it's not desirable, is a switch, where if the switch's MAC address table becomes overly full, it might fail open into operating like a hub, which is not a good thing. You'd rather want that appliance to maybe fail closed or fail secure. Now, when it comes to fail closed or fail secure, this is where we prioritize security under a fail condition. So something will go wrong, but security should not be significantly jeopardized, if at all, during the fail condition. But there is also another fail term, and a lot of people mix up fail secure with fail safe, and that irritates me. Because fail safe is where we prioritize security under a fail condition unless it's going to put human health, safety, and lives at risk. If human well-being and human lives are at risk during a fail condition, fail-safe will rather fail open. So, for example, if you have an electromagnetic lock on the door that gets normally unlocked by a keypad or an RFID card or biometrics or something like that, when there's no power, what happens? Battery backup. Cool. Carries on working like normal, right? Fantastic. What when the battery backup's not there or not working? What then? Well, you probably want it to fail open. Otherwise, you are going to have a door that will not open when there's no power. And if the building's caught fire, the power might go out in parts of the building, preventing people from escaping. So that's the difference between fail secure and fail safe. Fail secure prioritizes security under all fail conditions. Fail safe will prioritize security unless human health and safety comes into the equation, in which case then it fails open, because it's got to prioritize that. So those are the kind of attributes you want to look at and understand when it comes to looking at your network appliance. Is it an active or a passive device? Is it inline or off path? And what are its fail conditions like? And these attributes apply to every appliance. But there's obviously going to be other attributes we care about that are specific to the appliance. Like, for instance, firewalls. So firewalls obviously enforce rules for network transmissions. Now, in terms of the rules, firewalls can have a huge variety in terms of what they inspect. As I said earlier, your basic packet filtering firewalls, they are going to do the same thing your advanced ACLs do, which is source, destination, IP address, source, destination, port number, and protocol. But your more advanced firewalls can do much more rule inspection. They can look at applications, they could look at the encryption level, they could look at sequencing numbers for the transmission to make sure that it's all in order. There's a huge amount they can do. And believe me, there are entire courses and qualifications dedicated towards managing firewalls. So we're going to be very lightly touching on them, but hopefully giving you guys the foundation that you need to go further. So first of all, firewall rules might work in an order of ACL logic, where the first match is applied. Now, this does keep the firewall's processing pretty quick and pretty straightforward, but it does mean that the ordering of the rules matters quite significantly. Other kinds of firewalls might do a best match logic, where the firewall will compare the traffic to all of its rules and then apply the most appropriate one based on the one that matches the best. Downside to that, obviously, is it's going to take longer to do, but then rule ordering is less essential. Now, from a purely security perspective, I prefer best match. That way I can focus on writing good rules rather than the correct ordering of them. But from a performance perspective, the ACL ordering is much better. Now let's look at the types of firewalls. as previously introduced, we've got the basic packet filtering firewall. And as I've said, it is basic. Its focus is mostly on the IP header and the transport header so that it can pick up on IP addresses and port numbers, as well as the protocol. The benefit to packet filtering firewalls is they're quick, but they can be more easily evaded by an attacker. Then, your more advanced firewalls are collectively referred to as stateful inspection firewalls, and they work at layer 4 upwards. Now, different models and products will have differing layers. Some might be layer 5, some might be layer 7. It all depends on the individual firewall product you're looking at. But it is working at a higher layer, obviously, and is able to track session information and application details, which is going to be a lot harder for attackers to evade. But the setup and configuration of these firewalls is obviously going to be more involved, as you need to factor in all of those details. Otherwise, you have wasted your money and you might as well have bought a packet filtering firewall if you don't take advantage of these more advanced features. Another trade-off we have here as well is that they have got slower processing, which means they do introduce greater latency. Now, a fairly new advancement in firewall technology is a next generation firewall. And the reason why I do it in that condescending sound is because next generation firewalls evolved from unified threat management devices, or UTM devices. Now, what a UTM is it's a single appliance which we combine several network security appliances into one. Firewall, intrusion detection, intrusion prevention systems, which we're going to get to, proxy servers, which we're going to get to, VPN concentrators, which are sort of like remote access servers, but focus specifically on grabbing the VPN traffic and making it terminate in a particular part of your network. Network anti-malware engines, etc. Basically, a UTM rolls all these devices into one. But there are some problems with UTM devices, or at least problems as far as I'm concerned, and that they are fixed devices as far as functionality is concerned. If I buy a particular UTM device that's got a firewall, IDS, and proxy, that is all it will ever have. And also, the compute levels are fixed as well. So maybe you want a UTM device that has loads of features, but not necessarily high performance because you don't have that many users and that much traffic. Well, bad news. If you want all the functions, you've got to get the high performance UTM device. If you want to buy the UTM device that is more capable and suitable for your performance level, it might not have all the functions you want. And this is where next generation firewalls start to come into the equation. What a next generation firewall does is it allows you to control the functions you have by a license. So you'll normally get the NGFW with a firewall feature pre-built. And then you want the IDS capability, you buy a license, as and when you can afford to. Then maybe you want the network anti-malware feature. You buy the license as and when you can afford to. This is beneficial. So what do you need to pick then? Well, you just need to pick the compute level. What type of processing capability will you need to handle the traffic volumes this firewall is expected to experience? That is one of the big selling points to a next generation firewall. And personally, I like that capability. That I can pick the performance level I need and then license in the features I want. And what's also quite nice is I don't have to get all those features in one go. I can acquire them as and when my organization's finances and budget allows me to do so. A much better option. And you know it wouldn't be complete if we didn't mention the word cloud. Next generation firewalls do have better cloud integration. Normally you'll get things like, for example, the vendor identifies a new threat and they can create a new rule, and that rule gets distributed to all customers who have a valid cloud subscription, and then while you're fast asleep at night, that rule could be applied, protecting you from a zero-day threat, which I think is pretty freaking sweet. But we're not done with firewalls just yet. We also have something called a web application firewall. Now, as the name implies, it runs on a website on the web server. What it is inspecting is the HTTP request coming in on the website, focusing primarily on the HTML interactions and any executable instructions issued to an application running on your website. Those applications that give you, for example, those chatbots and some sort of interactivity on the web page without having to navigate to another page. Those are web applications. And usually the way they handle their operations is obviously they're inspecting the activity and they are comparing the activity to vulnerabilities that they have in a database. And this can be very, very helpful in many organizations nowadays, as websites are becoming the preferred front end for many services. And therefore, to have application capabilities, we have a lot of web apps running. Now, you might have even noticed some websites that you've gone to before mentioning this website is protected by insert antivirus company product. That's normally a web application firewall running on that website, and that little logo badge thing is there to give you the confidence that this site is being protected by a web application firewall and that your activity on the site is relatively safe. Then we get proxy servers. Excuse me. Now, before we look at the technicalities of a proxy, let's just use the dictionary definition of a proxy. A proxy is somebody that you nominate to do something on your behalf, especially when it comes to things that are important, like maybe voting on a decision or something like that. Well, in the case of a proxy server, what happens is the proxy server will receive a request from a client, and then the server makes the request itself on the internet, and it will receive the response. So basically, when a proxy server is running in your network, the end users, the clients, they're not going directly to the internet. They're going to the proxy server, and then the proxy server goes online for them, gets the content, and serves it to them. Now, this helps us in several ways. Firstly, the proxy server can, once the traffic has been determined not to be part of a block list, services. Then the proxy server goes and makes the request, gets the content back, and then it inspects the content once that response to make sure and it hasn't there is no once the traffic has been determined not to be part of a block list URL, but you probably do know the kind of proxy server goes and makes a request, gets the content back, and then it inspects the content going for you. Then, if that content contains a malicious payload, it'll hit the server and not the client. And pro tip here, it's a lot easier to make a server malware resistant than it is to make every client malware resistant. For example, my proxy server could run Linux, and malware is usually designed for Windows, not Linux. And it's a lot easier to make a Linux proxy server than it is to make a Linux client computer for every user. Now, what I've just described to you is something we refer to as a forward proxy. That's usually for clients making requests onto the internet. But you also get something called a reverse proxy. Now, the reverse proxy, this is more for remote users. The remote user connects through something like a VPN, and then their request to access an internal resource is actually sent to a proxy server that, after checking that this user is legit and is meant to have access to this resource, it goes and retrieves the internal content for the user, meaning that a remote user does not have direct access to internal content, even though they are coming in through a nice secure connection. And it just adds an extra layer of separation and defense between external entities and internal resources. That's fantastic. Now, in terms of implementing a proxy, for the most part, many organizations favor doing a forward proxy, and only a handful will ever look at really doing a reverse proxy due to the greater complexity. Now, when implementing a normal forward proxy, you would probably end up looking at doing a traditional or non-transparent proxy. Now, I call it traditional, but most people refer to it as non-transparent. And the reason why we've got such an awkward naming convention is because we didn't actually have to give this thing a name until a transparent proxy was created. So what's the difference? Well, with a traditional proxy, you normally have to tell the client the settings it needs to know. What's the IP address of the proxy server? What's the port numbers? Stuff like that. And then those settings need to be applied and enabled when the user is at work. And then if it's a laptop and the user takes that laptop home, they've got to turn those settings off so that they can use that laptop at home, because obviously the proxy server didn't magically follow them home. Whereas a transparent proxy, which is something I much more prefer, doesn't require any client settings. What happens with a transparent proxy is the network is set up in such a way that all user web requests get redirected to the proxy server, no settings required on the client. Which means that when the laptop is at work, the network forces the request to go to the proxy server. And then when the user takes that laptop home, well, there's no proxy at home, but also there's no settings forcing them to go to the proxy. Which means the user doesn't have to remember to turn something on or off, and it's a little bit trickier for users to try and bypass because they know nothing about the proxy server. So transparent's the way to go nowadays. But hey, if you're still running the traditional one, that's okay as well. Having it in either way is better than not having it at all. Now let's talk about one of my favorite devices, an intrusion detection system. Now what this bad boy does is it monitors network activity. It's normally an off-path device or tapped onto the network where you probably have a switch, and the interface that traffic's going through, or most traffic is going through, you configure that interface to be a mirror interface to the port that the IDS is connected to. That way the IDS gets a copy of all the traffic coming and going on that network. And the reason why you want it to be off-path is because it's looking at all the traffic and looking for malicious actions. Usually we implement these behind a firewall so that if something does somehow slip past the firewall, the IDS is able to identify that and potentially block it, which would be wonderful. But wait, how does the IDS know it's malicious? Well, it could use a signature database where it relies on predefined behaviors of this particular set of characteristics is malicious and this particular set of characteristics is not. The easiest way to understand signature definitions is to think about how we recognize animals. I could show you a picture of a dog and you would recognize it as a dog even if you don't know what the breed is, because there are certain attributes that you intrinsically recognize as being canine. While the same thing can be done with malicious actions on the network, there are certain attributes that regardless of what's being done are considered malicious. So it's pretty cool. The downside of signatures though is new attack techniques that haven't been documented will not be part of your signature database. And attackers, as long as they don't exhibit the signatures, will not trigger a signature-based IDS. Bonus though with the signature-based, it's very quick, it's very simple, it's very reliable. But you could look at heuristics as well. Heuristics is where the IDS starts to learn what's normal for your network and balances that with a little bit of signatures. And over time, the heuristic IDS will get very good at identifying things that don't fit your network activity. That's quite cool. But you do have that learning curve to go through where you've got to teach the IDS this is normal, this is not normal. Because it's going to flag anytime something abnormal happens, and abnormalities will happen for at least the first financial year. If you implement an IDS on a Monday, it'll freak out the first Saturday at the workplace when traffic levels are not normal. If you have a public holiday of some kind, or a bank holiday or whatever it's called in your country, the IDS will freak out because it's going to be expecting workloads during the week and is not getting that. So you do have to train it a little bit. Then you get anomaly-based. Now with anomaly-based, what happens is the IDS relies on what is normal for a protocol, and anything that is abnormal for that protocol is seen as malicious and triggers an alert. And the thing is, that's what an IDS does, is it just alerts you and logs you to the suspicious events. It requires a human being to respond to the alert, but that can be a good thing. I'll explain now. Before we get to that point, let's look at network versus host intrusion detection systems. A network intrusion detection system is obviously a network appliance, whereas a host IDS is an application installed on a machine and monitors the activity after the host-based firewall. Usually, if you're considering a host-based IDS or a software-based IDS, you'd probably implement that more on a server than a client because it's just not going to be viable to implement on every end user's machine. What'll make more sense if you want an IDS protecting end users would be a network-based one just before traffic gets into that network segment. But the IDS can be taken a step further with an IPS, or an intrusion prevention system. It works just like the IDS in terms of being off-path, monitoring activity, and user signature heuristics and anomaly-based detection. But it can actually do something about what it detects. Normally what will happen is the IPS will be set up in such a way with the rest of the network so that it can interrupt the communications or activities that are considered malicious, in addition to alerting you to that activity. Now, because it's able to engage with and control how the network behaves, it is more complex to implement. And my big concern with an IPS is that if it has a false positive, in other words, it recognizes something as being malicious that actually isn't, it is going to cause an unnecessary outage in the network because it's going to block something that shouldn't need to be blocked.
But in fairness to the IPS, it's able to identify and respond to a threat far faster than a human being can. Obviously, it costs more because it's able to do more. So that is another drawback on the IPS. And you get network and host-based ones as well, just like with the IDS. Now, given the choice, I generally prefer an intrusion detection system because it is cheaper, and many organizations do begrudge paying for security. Because security doesn't add value, it protects existing value. And the IDS requires a human being to respond. So if it's a false positive, the human being can identify that and choose to not respond, meaning no unnecessary outage, no unnecessary incident response process being invoked. But if the effectiveness of your security matters more, and you are able to tolerate the false positives leading to service outages, then the IPS might be right for you. It all depends. But a great thing is many intrusion detection systems are often able to be upgraded to an IPS with a license and obviously a bit more configuration and setup. All right, now another interesting thing we have is load balancers. Now with a load balancer, their job is to spread requests amongst multiple servers that work together. Normally we refer to those servers that work together to provide a single service as a cluster. So you could have several web servers working together, which means that if one web server is unavailable, the website carries on running on the surviving ones. But the problem with having a cluster is that you might have some web servers working and others doing nothing until the working ones have a failure. With load balancing, we're trying to spread that workload across them evenly. That way these redundant servers help justify their existence. Second benefit as well is with load balancing, it means the servers are able to handle a much larger workload than normal, which means it's a lot harder for an attacker to do a denial of service on us in any way or form, whether it be traditional denial of service or the more modern DDoS, distributed denial of service. So that's quite cool. Now load balancing can be done in several ways. You can do OSI layer 4 load balancing, where we're normally balancing the transport session information. So if I see session 1, session 2, session 3, session 4, I can spread those sessions across the redundant servers, which is pretty cool. Or you could have application level load balancing, where you're going to have the applications themselves managing the load balancing. So for example, if it was a web server, something like Apache or Nginx could run the load balancing itself. But you also do obviously get load balancing appliances that can do this for you in addition to that load balancing software. Generally, I do prefer having an appliance because it's normally going to be more efficient at spreading the workload. And also by separating it from the actual servers, it means that anything that goes haywire on the servers is less likely to affect the load balancing. Whereas having the load balancing taking place on the server itself, it's one thing that can go wrong and then mess with the ability for that service to be available. But regardless of which way you've decided to achieve load balancing, scheduling is also something that needs to be looked at. Now, with load balancing, you could do round-robin scheduling. The idea of round-robin is everyone gets a turn, regardless of anything else. Whether you are having a problem, whether you are a lower performing device, whatever, everyone gets a turn. Another approach is the least busy approach. Now, the benefit of least busy would be that maybe one device got a very involved request and the next device didn't. Well, the one that got the very involved request will probably still be busy, and round robin will not be fair to it. Whereas the one that's got the least work to deal with right now can take the work on. That's the benefit of least busy. It's going to lead to much more fair processing and latency. Or you could do waiting, where the first device gets 3 requests, the next device only gets 1, the device after gets 2 requests, based on the device's capabilities. That could be for waiting. Or you could let the devices gossip with each other by using the heartbeat-based load balancing. This will require that the servers do have a connection directly to each other so that they can keep an eye on each other's performance levels and status and stuff like that, and allows them to more easily spread the workload based on performance levels. Now that's the basic kinds of network security appliances and devices you want to be looking at. Let's move on to how we could make our network access a bit more secure. with VPNs and remote access. So let's start out with VPNs in general, understanding what they are. VPNs are a family of protocols, and this family of protocols will provide us the ability to have a stable route across an untrusted network. This is normally referred to as the tunnel aspect, or the tunneling protocol of a VPN. Then the VPN will add encryption to all traffic that passes through it or passes through that tunnel. That is usually referred to as the encapsulation service or encapsulation protocol. So visualizing that, what we have is our tunnel in pink there. Normally it's either a service or a protocol. And then you have your encapsulation that implies the encryption. It'll either be a service or a protocol. Depending on the exact VPN solution you choose, sometimes you'll use one protocol to do the tunneling and a separate protocol to do the encapsulation. Or in other cases, the VPN solution might be able to do both the tunneling and the encapsulation with one protocol, just using two different services within that protocol. And then once that is up and running, any traffic can be sent through it, that little yellow circle in the middle. And whether that traffic is encrypted or not, doesn't matter. The VPN's applying some encryption anyway. Ideally, though, it would be great if we could have both the encryption from the VPN and the original protocol going through it. Now, the benefit of a VPN is it does give you performance and protection in a fairly balanced way. But you've got to, again, look carefully at the protocols and what you intend to do with them. Because in some cases, the right combination of protocols will give you good performance, but maybe not the greatest protection. And in other cases, you might have great protection, but at the compromise of performance. It's a balancing act that you've got to find and go with. This is why you want to carefully read into the protocols and look at how they're intended to be used. Now, in terms of getting your hands on VPNs, you can get commercial VPNs. I'm sure you've often seen other creators on YouTube doing sponsored readouts for various VPN services you can pay for, and they do offer some benefits. First and foremost, they will offer the average consumer the ability to have a more secure connection, which can be very useful if you tend to use public Wi-Fi quite a bit. And also, it does give you the interesting advantage of a VPN makes it look like you are connected to the internet wherever the tunnel ends. And that applies to enterprise VPNs as well. With a commercial one, you could appear to be in the US, in Australia, in Japan, you name it. With a commercial VPN, you can decide to look like you are anywhere in particular. But with enterprise VPNs, we normally implement these for the workplace for more secure access. Oftentimes for remote users, but sometimes something else. Ooh, what could that something else be? Well, let's check out the VPN types. Remote access is probably the most common example for enterprise usage. And this is normally there for a user who needs to access the workplace from a remote location, like from their home. The VPN, in red, would run from their computer all the way to a remote access server at the workplace. And then all their requests will go through that VPN to the remote access server and then off to wherever they need to go, whether it be a server local or maybe a site on the internet. Which is why when an employee is busy using a remote access server and a VPN, they will not be able to go to websites and services online that would normally be blocked at the workplace, because their request to go to, for example, facebook.com, which might be blocked at the office, is going through the VPN to the office, and then it gets blocked on the way out. But when they turn their VPN off, they'll be able to go to Facebook, because obviously they're not being subjected to any traffic filtering in the enterprise network. Then you get your site-to-site VPNs. Now this is where an organization might have two locations and they're using an ordinary internet connection and a permanent VPN between those two locations to transmit enterprise data. So you might have Site 1 and Site 2 with a site-to-site VPN server at each, which has a permanent VPN running all the time. And then clients and servers at Site 1 can send traffic to clients and servers in Site 2 through a permanent VPN. This is actually done more and more often, as it's a lot cheaper to have an ordinary internet connection than to have a more elegant and sophisticated enterprise WAN connection, which normally comes at a greater cost. And you also get more flexibility as you can flip between different types of internet connections and just require that site-to-site VPN connection to get re-established. So it's quite nice for fault tolerance. But let's have a look at some VPN protocols that you want to know about. Now there's actually quite a lot of them, but the modern ones you want to be aware of are TLS tunneling. And with TLS tunneling, what happens is we're using TLS encryption, the same kind of encryption we could use for HTTPS, to encrypt the data traffic and create a tunnel. Fantastic. But the big advantage to TLS tunneling is, unlike older encryption protocols, TLS tunneling also encrypts the VPN authentication information, which is not something done with the older protocols like L2TP or the point-to-point tunneling protocol, PPTP. TLS tunneling is also able to run over TCP or UDP, which gives us an advantage. The downside, though, with UDP is it does make it more prone to DDoS attacks, but it does give us a faster connection. So if you want a fairly secure and low latency VPN, TLS tunneling can give that to you because of the inherent performance benefits of using UDP. Or if you favor greater security, then you could go for TLS tunneling over TCP. So choice is yours. You can also use IPsec. Yep, it popped up again. IPsec has two modes of operation. Its default mode of operation is transport mode. And what it does is it encrypts the payload and then just forwards it as a packet. Simple as that. We refer to that as host-to-host security. But IPsec also has this thing called tunnel mode, which can be used for site-to-site security. With tunnel mode, what happens is we take a normal IPsec packet where we encrypt the payload, add an authentication header and stuff like that. And then the whole packet becomes a new payload in a new packet. And that new payload gets encrypted, and a new authentication header is added, and different IP information can be included in that new IP header. That would be great for a site-to-site tunnel. So IPsec's pretty cool for that. But the go-to option that everybody wants to use right now is the Internet Key Exchange, or IKE. It's becoming very, very popular for a few reasons. Firstly, it integrates very well with public key infrastructure and digital certificates, making for a much more elegant and seamless VPN solution that doesn't require users to always have to type in credentials, yet still offering adequate authentication capabilities. But you can go with pre-shared keys if that's more your thing. And IKE has two versions. Version 1 offers great host-to-host and site-to-site security without too much setup involved. And IKE v2 is very good for client-to-site, which is great for a remote access VPN. So you've got those going for you. But honestly, you could still be using any of the older VPN protocols like L2TP, point-to-point tunneling protocol, MS-CHAP v2. There's a whole bunch out there. And you know what? Any VPN is better than no VPN. But once you have one, it's definitely worth moving towards one of the more modern solutions. And I do use the term modern relatively here, obviously. But VPNs aren't the only thing we need for remote access. We could also look at doing remote desktoping. Now, remote desktoping is obviously important for IT support as it allows us to remotely access another machine's graphical user interface to either work with it or troubleshoot it. Now, we could use the remote desktop protocol, which was pioneered by Microsoft, but bless Microsoft, they've started to make RDP available to other vendors. So you can use something like, for example, XRDP with Linux, which I think is pretty freaking awesome. But if RDP is not your thing, you could look at using VNC, the Virtual Network Connection. Some people refer to it as the Visual Network Connection. Either way, it's another remote GUI service. And it's got a very interesting advantage over something like RDP. RDP, you will notice you're doing it remotely because it's going to be very, very laggy, and the quality is going to be quite low because RDP is trying to refresh the entire user interface all the time. VNC improves performance by only refreshing the part of the user interface that is being updated right now. So unless you have a full screen change, VNC will be quite minimal in terms of the updating. But VNC is a little bit more likely to have problems. Like, for instance, there is a lot of variations of VNC, and that can lead to incompatibility and some configuration challenges. And then you have HTML5, clientless RDP, or basically remote desktoping through a website. HTML5 does support the ability to remotely control another system's user interface, and that can be pretty useful, but also possibly risky as there are loads of HTML exploits. But usually it's the tool that dictates the protocol you're going to be using. So with native tools, if you're using something like Microsoft's Remote Desktop Connection utility, you're going to be using RDP. If you are using something like tight VNC, obviously using VNC. But you know what? You're not limited to using a native tool that comes with any given operating system. You can use a variety of third-party tools. Things like TeamViewer or AnyDesk are two very good options for third-party tools. And in my experience, a lot of IT professionals enjoy using one of those two tools. Personally, I'm a little bit more inclined towards AnyDesk, but each to their own. TeamViewer has got its advantages and disadvantages, and AnyDesk has their own. And in case you're wondering, no, neither of them are paying me any money. It's just two that I've encountered quite often. I don't mind talking about two different tools as long as I've got two different tools to talk about and they're fairly equal in terms of what they do. Your choice entirely. Then, we also need to consider remote command line administration. With remote command line administration, we are able to remotely access a system and use the various commands on it. Now, here's the thing. As IT professionals and administrators, we shouldn't be afraid of commands. We should be getting comfortable with commands, because commands can often achieve a lot in a very small amount of time compared to trying to do anything through a graphical user interface. Also, commands are purely text data, and text travels way quicker than any other kind of data. If you use WhatsApp, for example, you've probably seen that when you send a text message and a picture, or better yet, let's do a picture first and then a text message separately, you'll normally get a double tick on that text message before you do on that picture or video, because text data is quicker to transmit than multimedia data. We're talking bytes, maybe kilobytes of data versus megabytes of data for multimedia. So that means that remote command line administration is going to be very low latency and not take away too much bandwidth from the users, which is good for us. Now, what do we have to work with here? Well, Telnet was our first option for remote command line administration, but there's a big problem with Telnet, and that is it lacks encryption, and there's no way to add encryption with Telnet. Oh dear. Now, this means that Telnet sends everything in clear text. If I'm able to intercept a Telnet communication session, I can reassemble the session and see everything that was typed. Every single thing. I mean, one of the biggest jokes is when you remotely log into a machine with Telnet that asks you to type in a password, Telnet won't even show you a dot or an asterisk or anything like that to indicate how many characters you've typed, okay, as a legitimate user. But as an attacker trying to eavesdrop over your session, I will not only see the keystrokes, but I will see the password you've typed in. That's kind of ridiculous. And sadly, Telnet being a very old protocol, it wasn't designed to be extensible or enhanced in any way. So we can't exactly go and add like SSL or TLS encryption to it like we do with other protocols. This is why Secure Shell, or SSH, was developed. SSH does what Telnet does, except it does it with encryption. And it was also designed to be very, very extensible, which means that it can be used to encrypt other protocols. Let's use FTP as an example. You get FTPS and you get SFTP. Now, normally when the S is at the beginning and the S is for security, that normally implies we're using Secure Shell to do the encryption, which is pretty cool. Now, Telnet not having encryption is not necessarily a bad thing. As long as you are using it across a secure and trusted network, nothing wrong with Telnet. But Secure Shell would still be better. Let me give you an example. If I'm at the office and I can use Telnet to remote into, let's say, a router to configure it, I'm probably going over a trusted network, in which case it's not too much of a risk to use the unencrypted Telnet. And if I'm working from home and I need to remote into that router, and I could use SSH to do so, that would make sense because I'm going over the internet, an untrusted network. But I would still rather use SSH even if I'm at the office, even if I'm on a trusted network, for one big reason. Then I don't have to think about, am I on a trusted network where I can use Telnet, or am I on an untrusted network where I should use SSH? If I use SSH, regardless of the type of network I'm on, I'm always going to be in a better situation. Now, for operating systems that don't support Secure Shell out of the box, like Microsoft Windows, for example, you can install OpenSSH client and server applications without too much difficulty. It's mainly the OpenSSH server that's the big issue with Microsoft. Otherwise, everything else in the world supports SSH, or should at least support SSH. Moving along, for remote administration, a very cool idea is out-of-band management, or OOB Management. Now, with out-of-band management, what's happening here is this. We're going to have dedicated infrastructure that will allow an administrator to access a device from a completely separate network infrastructure. So over here, we've got a very simple network, a router, a switch, a bunch of servers, and a bunch of laptops. Now, the blue lines there are your normal data network. The orange lines with that workstation there, that would be a separate network infrastructure for remote administration. Now, the benefit of such a design is that if an attacker were to compromise the data network, the blue network, they would not be able to administratively control the devices because obviously data network would be set up in such a way that no administration could be done through it. And only device administration, like for example servers and network appliances, would be done through the out-of-band management infrastructure, the orange network. And the chance of the attacker compromising both networks is a lot lower than if we relied on one network for both data and administration. But for administration, we could also have jump servers where that workstation could be internet connected to allow for remote access to this out-of-band infrastructure. Would this drive your costs up? Of course it would. Would this be an ideal solution to your network administration? Not necessarily. Could it add value though? Yes. Honestly, when it comes to network design practices, there's a lot of freedom in achieving a secure network design. There are some principles that want to be observed and followed. And you might be wondering, but at no point have you shown me a properly big network topology, and I know I haven't. In this module, we've just laid the foundations here. We are going to build on this in a later module and in later video series. But for now, we've gone through a few devices, a few design concepts in general, help a lot with network security. Now, I'd like to thank you all for watching, and if you haven't already subscribed, please do so. If you've got any friends or family members that would be interested in this kind of thing, don't be afraid to share it with them. And I will see you all in the next video.